Okay, maybe I could like tell everyone, or like maybe also put it in the chat if for someone in like later. Uh, maybe. Okay, yeah, I'm sending out the message to everyone. Okay, so hi everyone. You are everyone's welcome here, and you can keep your video turned on if you wish, or else if you want to keep it turned off, that's also totally fine. But feel free to speak with each other through the chat or ask questions during the meeting and communicate with each other just like how it would be in a normal real life face-to-face journal club. And anyone, feel free to introduce yourselves. Would anyone like to start introducing themselves, like one by one if you wish to? Like you could say whether you are new to this field or how you felt when you read the paper, things that you want to share with others. Yes, like for the questions, like we will be removing your audio because we do know that privacy is important. So we won't include any of your audios or pictures or names, anything that's linked to you. The only thing that will be on the video will be like the team, us, the presentation. Uh, we will speak more about how the sessions will be organized in a few minutes.
Okay. Shall I introduce myself?
Yeah, sure, of course.
Just to break ice. My name is Jacopo. I'm from Italy, and I just graduated in December. I graduated from my bachelor degree in physics in Trieste, and hopefully from September 2021, I'm starting a master in quantum science and technologies and Munich. At Munich. I'm applying in these days, so I don't know if they
Yeah.
will take me. But very interested in the field, and I hope that you can push us to read papers to keep on the top notch of the arguments, so we can keep updated.
Cool. So I think I could also start. Alberto, I think you could also say something till we wait for the others to join. I'm Bavitra. I'm also like a physics student. I'm doing my master's in quantum technology at EWT Aachen. Uh, we organized this mainly to get the beginners into the quantum technology scene. There is one advantage the field quantum computing in general has over the others because the research is quite new. It's not like 2 3 years new, it's still like 1 or 2 decades new. So a lot of the papers that are available are actually very accessible to read for even for a newcomer. And to make sure that you are ready for the research scene, you should keep yourself updated with the research papers. And uh, we wanted to introduce a lot of people into reading the research papers as much as possible because this is an extremely research intensive field at the moment. It has not completely reached the industry yet, it's still like halfway through. So it is very important that if someone who wants to have a career in quantum technology, especially, it's really important that they are able to understand the research, the ongoing research, because it's a rapidly changing field. And that is kind of our aim to help beginners get started with this. And for anyone who doesn't know about QUE, we all met up last year during the Kiskit Global Summer School. Lia, she was the founder, and she reached out to a few of us, and we all got together, and we are still in the process of building this. And we have had a couple of community events, Christmas event, and this general club has been in the plans for a few months now, and so we are kickstarting now. Uh, I think Lia is here. Lia, do you wanna like introduce yourself?
Yeah, can I be heard? Testing?
Yeah.
Oh, perfect. Okay. I wasn't sure if my mic worked. Hello, I'm Leah. I'm currently, I guess I'll introduce myself. Thank you all for joining the Journal Club. Yeah, I guess I'm one of the admins, like Babita and Alberto here, who run the Discord server. So it's a Discord server for, it's called Quantum Universal Education, because the idea is that quantum information science is like a really big field, and so people from all different fields, all different levels can come together and learn about all different aspects from each other. So thanks for joining our journal club. To introduce myself, I'm currently a PhD student at the University of Oxford doing quantum computer architecture research, kind of more diagrammatic quantum computing research. Now I've recently started doing quantum natural language processing, although I'm new to it. Yeah. And I did my undergrad and graduated undergrad in 2020. So I'm probably not same age as some of you, a few years older, a few years younger than most of you. So actually that gives no information, but okay.
No, that's just me.
Yeah, is that all right? Anything else for me, sir?
Alberto, maybe. Would you like to introduce yourself? I don't think we can see your face. It's kind of cropped.
Yeah, I have problem with my webcam. But, well, I don't know. Let me think.
It's okay.
Well, I'm Alberto. I'm a PhD student in Mexico. I will start my PhD about quantum machine learning. And I don't know. I only help with this, with the video record. So I think it's all.
Oh, Alberto, we see you on two screens. One screen, we only see your shirt, which is really cool, and we don't see your face.
Actually,
oh, perfect.
Okay, now, yeah. It's perfect.
You fixed it. Yeah, there you go.
Okay.
So, shall we begin, or do you want to wait for 5 more minutes for the others to join? Maybe like 4 more minutes. We can wait till 17:50. I'm like, yeah. So, for others to join.
In the meantime, can I ask where y'all are from?
Yeah.
You can just stick it in chat, or if you can unmute. I think I hear echo. I think, Alberto, your mic's echoing.
Oh, Mexico.
Could we also get a sense of like what like what year of students you are? Say like what year of high school, undergrad, grad student, etc. This is just so we can get a sense of what audiences there are and how we can split up. We want to do breakout rooms in future journal clubs. This is the first one, so we just for this one we'll walk you through the format of a journal club and how to discuss. But for future ones, we will break you up into rooms and you can discuss with each other and learn from each other.
quantum sensing or cryptography. Is anyone in that field? I am not near quantum sensing or cryptography. I am more into applied quantum computing. So anyone? Feel free to talk with each other in chat. Some people are having trouble connecting, so I'm just gonna send the link.
Oh, we have a new area of our webpage that's different areas of quantum computing. We want to make a personality quiz for this, but this is like always a work in progress. Oh, I'll include the HTTPS link. Here we go. So it's our new webpage homepage, and the idea is that at the bottom you'll have different links of areas of quantum science, and we're looking for people to write, say, like curated intro links for each area. So I think it's like 12 or 13 different areas, which is quite a lot. And the idea is to sort the links by difficulty level and have a person who is like, say, a student or researcher in each topic, right? Like just make a list of links for people who are not in that topic. And just because there's so many different areas of quantum information science, and like people who are experts in some areas often cannot communicate with people who are experts in other areas, even though they're all quantum scientists. It's quite funny.
So I think we are ready to begin. I'll try sharing my screen now. Can someone tell me whether they are seeing my slides? Because I really have no idea. So I think we can begin. Welcome everyone. So for the ones who joined just a while back, this is our first session on a journal club on quantum technology. We are trying to touch different fields in quantum technology, varying from quantum cryptography, sensing, applied algorithms, quantum computing for finance, hardware, and everything, so that a lot of students who are just starting in the field can get an idea of what the different fields are and probably make a choice for themselves if they wish to pursue in this field. And for our first session, we are going to look at the conjugate coding paper by Stephen Wiesner. It is actually the first paper to bring these ideas. It was written even before Richard Feynman made his very first talk about simulating physics processors with a quantum device. But he couldn't actually get this thing published in the 1970s when he actually first wrote it. So he published it later on in the 1980s. So this is actually like the first seeds of the field of quantum computing. So we believe that this would be a very good first paper for us to look through. And I want everyone to know that this is a safe space. Feel free to ask questions and feel free to interact with everyone here. And don't hesitate thinking that this is just an online thing or a webinar where you just like sit on mute, turn off your videos and just listen. This first session will be just an introduction where our founder Lia, she will be showing how to present a paper, and it's more like an introduction where she shows how a journal club is run. And then for the next sessions, we are planning to do it on Zoom, where we could have breakout rooms and have a communication between all of us and make this a much more enriching experience than just having it as some kind of webinar. And also to let everyone know that these sessions will be recorded and it will be made available on our YouTube in case you are unable to participate. But do not worry about privacy, because we will make sure that your videos, your names, or any kind of data associated with you, they will be removed before being uploaded. So in case you miss one of the sessions, you can always join back. And for the schedule, we are planning to do one paper every month on the first Saturday. The time is going to be the same from 3 to 5 in GMT, without taking into account the summertime. Only today's session is on Google Meet. From the next sessions, it will be on Zoom, for which we will give you the link. And this is our YouTube channel where you can find the recorded videos later on. And we are planning to continue the communication only via a Discord channel and not through emails, because there were a lot of problems with reaching to people who gave their university email addresses, because the email got they ended up in spam. All the files, all the relevant details will be communicated via Discord. And then the next cool thing is you could see that Alberto and I are wearing a very cool t-shirt with featuring our cat. And if you want to have one as well, you could become a contributor or else a curator at Full Stack Quantum Computation. This is a work in progress, so we are just now beginning. We still have a lot of ground to cover in terms of beginner-friendly material. But if you wish to become a contributor to open source education, feel free to get in touch. And you will, if you sign up to become a contributor or a curator, you will also get a cool t-shirt like this featuring our cat. And do not worry if you feel that you cannot start writing content right now and you are just learning it. Still, you could check out our website. There are a lot of good articles, tutorials. They are like ranging from Cascade to Silk. There are some of a lot of our contributors and curators. They wrote these with examples, and we were able to reach out to some professors in different universities. They were also willing to share their notes. And if you want to make an initiative at your own institute, your university, feel free to do that and let us know. And if you are learning something very new and you found something exciting that actually cleared one of your questions you had about quantum computation, write it up, start writing an article. Do not worry if you feel that you are a professional in that field yet. There are a lot of people on our server who are like specialized in different parts. So if you are interested in writing something, you can contact us and we will help you find someone who is a professional in that field, and you could get the help from them to finish writing your article. And then for the outline of the event, today we will just start by introducing the paper and discussion, and Lia will follow up with the discussion of the scavenger hunt. That whole scavenger hunt idea was intended to help beginners who don't have experience with reading papers, because they can be very dense in information, and processing that much information is usually hard for someone who's just beginning. So that was to actually help people to kind of like spot the important informations on how to read the paper, etc. But the future sessions, we will also make sure that we keep helping the beginners, but at the same time, we will try to make it as interactive as possible. So you can talk with each other, question things, question the proofs, find out whys and hows. Since this is an interdisciplinary field, bridging like physics, computer science, mathematics, it's more useful when everyone like helps another person and explain, because that also improves your own understanding. So today's session, it will be moderated by Lia. She introduced herself before. She has a background in physics. She did her undergraduate at University of California, Santa Barbara. And now she's at the University of Oxford doing her PhD in the group of quantum computing, with her main focus on like Qt-ZX calculus, compositional distributional semantics for NLP. And she also founded the people interested in quantum universal education. We have been doing this for like about an year now. And she started the website, and she has been in Cascade as advocate since 2019, and also interned at IBM-Q. And she also contributes a lot to the IEEE Quantum Education and Quantum Initiative. She founded the WomanX Hacks, and the hackathon, which is going to happen next weekend, but unfortunately the registration is closed, but I'm pretty sure there are a lot of events planned for it. And she was also the teaching assistant for the Qubit by Qubit that happened last semester. And I have attended quite a lot of her presentations, so I know for a fact that she makes really engaging presentations. So let's see what she has today. And with that, I'm handing over to Leah.
Thank you. Wow, that's a that's a very long slide. Pavita, can I ask where the scavenger hunt is? I think I don't have a link. I have, like the draft version, which is not as pretty as the real version.
Yeah,
I didn't find it either.
on the Google Calendar event attachments, but I don't think whether it's visible for everyone.
Let's do that.
But I could send it to you again if you want.
Yeah, no worries if you haven't gotten it yet. We'll find it now.
Like, I'll send it to you on Discord just in case you want to share the screen while you're like speaking about it. Because I'm unable to send any files with the Google Meet. Okay.
Does the link I just sent in chat work? I think so. All right. So I think how I'm going to do this is share the paper on one side and then the scavenger hunt on the other side. I'll leave the scavenger hunt blank so you can think about the questions, and we'll just talk through the questions together. The idea is that the scavenger hunt will set an outline to pace us and ask us what are the more important questions to think about for the paper, so it's not just like a lot of words all at once. I'll give a few seconds for everyone to open up the PDF that was just linked in Discord and also sent via the link via chat.
If you don't mind, I forgot to mention something a while back. Can I just say that?
You're sure.
I missed out one important thing. I want everyone to know that this is not just restricted to us presenting papers. This is an event for everyone who's here. So if you want to present a paper yourself to do one of the sessions on a topic that you like, you are more than welcome to do that. You can start with the paper, just present it, just like it, be a moderator. And for the topics of the upcoming papers, we will start having a poll-like system where we suggest a few papers and you can pick what you like. And if you have any specific paper that you want to look into, you could also send us the suggestions on our Discord channel and we will look into that. But for the first few weeks, we are looking for things that are basic. Usually during the first 2 decades of the quantum computing, where a lot of the new exciting results came out, and also they are very easy to read. So this is just to get everyone up to the same level so everyone can have a conversation going on. And afterwards, we can start looking into much more deeper papers. So if you're interested in presenting something, just to let us know, because it is a very good opportunity for you to see how scientific communication works. And this is definitely not in a university setting where you have the pressure of being graded or you have to worry about professors saying something. So this is a very chill atmosphere and you can totally ask our help for doing something like this. And if you are an undergraduate student or high school student, journal clubs or presenting a paper is not something like an opportunity that you usually come across. So you can use this. And if you want to present a paper, just you can directly contact me on Discord. And that was it.
Yeah. Thanks, Vanita. Thanks, Alberto, for setting this up. So I guess we'll start now. I'm sharing. I think I'm sharing my screen, correct? I'll need a yes or no. Okay. Am I sharing?
I don't see it.
Oh, okay, let me try again. My screen froze. My screen is stuck. Sorry, give me a sec. And it says I'm sharing my screen.
I think Leah is still having difficulties, so in the meantime, I think everyone has their videos turned off. That's fine. So the ones who join new, would you like to introduce yourselves? Like tell something about your background, or do you have any questions? You could tell us how was your experience with reading the first paper if you are from, let's say, high school. Yeah, it's back. Yeah, okay.
Okay, I'm back. Yeah.
Yeah.
My screen froze. I will try again. Hopefully this will work. Okay, did that work?
Yes.
Yes.
Oh, phew. Thank goodness. All right, now I try to. Yay! So I think now both sides of my screen are visible. Thanks for your patience, everyone. I think first I should explain what a journal club is. So if this is like the first time you're hearing what is a journal club, that so you can get a sense of it. So at least my impression of what a journal club is that you can be in a group of people, could be people who are students just like you, it's around the same level, or it could be a research group where some people say you're PIs or multiple professors and grad students and undergrads all together in the same group. Just people from the same department or interested in the same topics. And usually a journal club has a focus of some field in mind. And every time the journal club meets, one or more people present about one paper or have read about one paper and present it to the rest of the group, or everyone reads that paper and discusses it together. So it can be organized many different ways, but the idea is that it can be a way for students who, especially who have never done research or don't know as much about how to read a paper, because it could definitely be a bit of a learning curve when you first start reading papers. It's a way to read and understand as a group. For those of you who are taking the first time look at the scavenger hunt, it's on my right-hand side of my screen. I think that's okay. So there's a lot of margins on this page so that you can write down notes here. It's nice if you print it, or if it's a PDF, you can open it up in a PDF viewer. Say, I think Adobe Acrobat on your computer will work, and you can write in the margins. The first note here is that reading a paper isn't like reading most other things that you've probably read up to this point. So like articles or book series, watching movies, like usually those are quite sequential and you just go through that. But for a paper, you don't have to go through it in order. It's actually, although this wasn't intended, this paper called Conjugate Coding is a perfect example, because the famous part of this paper is the second half, the quantum money part. There's little reference to the quantum communication in the first half of the paper. It's not as influential on the field of quantum computing. But yeah, this seminal paper did define the field of quantum cryptography and is arguably the first relevant quantum cryptography paper. So the way I'd like to organize this, though, is that we can just go through the questions, and I highly encourage all of you to, if you know the answer to the question, you can just unmute yourself and just go ahead and answer. I think we have the number of people we have currently will work so that anyone can just unmute and answer. And just be respectful if someone else is currently speaking. Try not to interrupt them. I highly encourage us to use more as a discussion way, so it's not just me reciting things. I think we'll all learn from that. There's no dumb questions and there's no dumb answers. So yeah, I think you can just get started. So we do, although the paper has kind of two halves, the example 1 and example 2, we'll just focus on example 2 because of the historical relevance. But example 1 is still really interesting to read. It talks about different ways of encoding physically the qubits and some quantum communication. But example 2 is the quantum money part. So we'll start with some questions at the bottom of page 83, so up to here. If this example 2 starts on page 83. Could someone answer what are A, B, alpha, and beta when you have your quantum money system. You could just unmute and speak.
A and B and alpha and beta are two separate orthonormal eigen base representations of the state that the system is in, or the individual particles that you transmit.
Thanks, Dills, for responding. Yeah, so A and B are orthonormal to each other, and then alpha and beta are orthonormal to each other. And A and B and alpha and beta, those pairs of orthonormal basis states, are complementary to each other. So what that means is that if you measure one of, well, actually that's question 3, so I won't say it. Could someone answer questions 2 and 3 about what's the relation of A, B, and alpha and beta?
So A and B are both kind of paired to describe the whole system with in terms of one quantity, or like in terms of, you know, the one aspect, and then you can also describe the system with alpha and beta together, but you cannot do that with both at the same time, or you can't measure them both at the same time because it like doesn't work quantum mechanically.
Moreover, they are particularly symmetric because if you are in alpha or beta, you have a half 0.5 of probability to be in A or B, and it is the same for A and B. You have a 0.5 probability to be in alpha or beta.
Yeah, that's good. That's good answers. So I'll show on my screen now, I'm sharing screen, how to solve for A and B in terms of alpha and beta, just so if how you think is more in an equation sense, then you can see. So I'll need my pen. We have on the paper alpha is 1 over square root of 2a plus b. And we also have the same thing for beta, but it's the minus sign. Something really cool for qubits is that you can do the same thing except expressing A and B in terms of alpha and beta. So you can get, if you add up alpha and beta together, then alpha plus beta is equal to 2 over square root of 2, so 1 over square root of 2a. So is equal to, sorry, 2 over square root of 2 over 1a. So a is equal to, a is equal to 1 over square root of 2 alpha plus beta, and then b is equal to 1 over square root of 2 alpha minus beta. So sometimes in UV papers, you'll have to do some of these math in the margins if they don't show all the steps. But this means that if you were to measure A and B in the alpha beta basis, you'll get this coefficient squared, or I guess A and B. Yeah, and A and B in the alpha beta basis, you'll get alpha with probability this coefficient squared, so half, and then you'll get beta with probability this coefficient squared, which is half. And same with So if you measure in the wrong basis, if you measure alpha in the alpha beta basis, you'll always get alpha with assuming no error. But if you measure alpha in the AB basis, then you'll see the result A half the time and you'll see the result B half the time. So you won't actually know that the state was actually alpha in the first place. You might see, so in a common example is, let's say, you might have seen these states a lot in quantum computing in qubits. Here's just examples of what you could choose for alpha and beta. Where the matrices for these things are 1, 0, 0, 0, 1, 1 over square root of 2, okay. 1, 1, and 1 over 1, -1. So those are just examples of what states you could choose for alpha, beta, in A and B, 0, 1, plus or minus. But you don't have to choose those ones. Just any two that are orthogonal. To visualize on a block sphere, so a block sphere is just a sphere. So I just draw it as a circle, but technically it's a sphere. So a 3D circle. You can have the 0 state up here, and so in the block sphere, you multiply all angles by 2. So when I say, when you think of the words orthogonal in linear algebra, they're perpendicular to each other. So 90 degrees between those two vectors. But on the block sphere, you multiply the the angles between all vectors by 2, so that instead of these two vectors, 0 and 1, that were originally perpendicular to each other, are now directly across, so that the angle between them is 180 degrees instead of 90 degrees. And then you could say that the plus state is on the equator, well, relative to the block sphere. For example, this could work. You can have the plus state on the left side or the right side. It doesn't really matter, as there's different conventions, as long as you get that they're orthogonal to each other, so across from each other. And you can think of, if you do it a measurement when you visualize in the block sphere, that your state vector, which I'll use a different color. Can I use a different color? Change color. Yeah. So if your vector was originally here, and then you measured in the 0, 1 basis, you'll just get 0. But if you were to measure it in the plus minus basis, you'll see the result plus with half probability, and you'll see the result minus with half probability, because it's on the equator relative to 0 and 1. That's just how quantum mechanics works. But you also see this, so although we are only using like symbols like 0, 1, plus and minus here, you could also imagine quantities to be physical quantities. So you could, like in the first part, they talk about encoding photons. So you can encode the phase or polarization of photons. Those are two different ways to encode a quantum state inside of photons for quantum communication. So if you've seen experiments with a polarizer, that's like when you have sunglasses, you might have polarized sunglasses, and then you can have a film. And if the film has a direction associated with it, so if you have two polarizing sheets that are linearly polarized, that are parallel, so with each other, there will be light passing through. And if you turn one of them 90 degrees to the other, then there will be no light that passes through, which is really cool. Anyway, but I digress. So we're going back here. So the next question with the scavenger hunt is, if instead of 20 digits, which was the number of digits for the quantum money scheme in the proposal, if you had two random binary sequences that were, like the number of digits was 5 instead of 20, what would be the respective states of the isolated systems? Would someone be willing to share their screen to present this part?
Hello. I can share when I explain this when I want
Go
to.
ahead. I'll stop presenting so you can do that. While she's sharing screen, I can answer questions in chat, or anyone can.
Is it visible? Yeah.
Yeah, your screen is shared.
Yeah. So the two sequences that are given are M is 0 1 1 0 1 and N is 1 1 0 1 1. So if M is 0, if if I can't highlight, I don't have anything to highlight. Hopefully you can understand. If M is 0 and there are two partitions where that is if N is 0, then we'll get the state A, and if N is 1, we'll get the state B. So for the first bit, M is 0, so we'll go to the upper branch, and then N is 1, so we will then branch downwards, so we'll get the state B. So this is one state, and then for the next one, M is 1, so we will branch downwards, and then for N is equals to 1, we'll get the state beta. Am I correct? Is my approach correct? Hello?
Yeah, it's going great. Keep going.
Okay, so similarly for the third bit, M is 1, so and N is 0, so we will get the state alpha. I think this should be alpha instead of, it's given delta here, so that so it should be alpha. And then for the fourth bit, if M is 0 and N is 1, so we'll get the state beta. And for the last one, M is 1 and N is 1, so we'll get the state beta. So the 5 states will be beta, B, beta, alpha, B, and beta.
That's good. Yay, thank you. I think now would be a good time to get a summary of the first part of the protocol, so of quantum money. If anyone would like to give a stab at that. Just what you think the protocol is, step by step.
So basically, you encode the money while you print it with a like secret quantum state that is not really changing because you manipulate the properties or whatever, and you print a serial number on it so you can recognize later which exact bill it was. And then when you take the money back, then you can always, because you know the serial number, because it's written on it, you can then measure the exact correct bits that you encoded before on the money. And then, so for example, if the first bit you encoded in the AB basis, then you can like read the AB value and it's always going to give the right answer. And if the second bit then is encoded in the alpha beta basis, you can read it in that basis. And it's also going to give the right answer. But anybody else can't read it because they don't know which exact basis they need to measure it in.
Yeah, thanks. Oh, that's really good. That we have a question in chat about not understanding. I think we can. This is a chance. So this is a learning opportunity because then you can ask about which parts you don't understand, and then we'll figure that out together. Yeah, that's a good observation. This is BB84 was directly based off of this paper. So this idea. So BB84 is sometimes people referred to as the first quantum cryptography paper, but technically this one came before, but it wasn't published for over a decade after it was written. So this one was technically published in 83, but the paper had been circulating for a decade before, but unpublished. The Wikipedia page of the author is really interesting, actually. So instead of the goal of, it's actually the exact same idea, except instead of the goal of BB84 being to send a secret to agree on quantum key distribution, so two people agree on a secret shared between them so that they can share later more secrets between them, secret messages between them using that secret key that they had before, had distributed between them before that other people don't know. In this case, it's sharing, it's having quantum money. So it's that an individual and a bank know.
Can I just ask one question? Because okay, I wasn't really sure I understood like what they do with this serial number. What's the point of that, and what do they do with it?
Yeah. So the important part here is that the secret is the bases. So let me see if I can find the right part of the paper to answer that. So although I do agree that the paper did not write as clearly exactly what is going on with the serial number. Actually, let me just see where it doesn't say here. So you can have, so you generate 2 bits for each number, because each number, each digit of each, I say digit, but each of the 20 qubits can be encoded in one of these 4 states. And so you need, since there's 4 states, you have 2 bits to choose which of the 4 states it is. And one of these 2 bits encodes which basis. That's this MI here. So you either choose the AB basis or the alpha beta basis. And then you also have an NI, which is which state it is within that basis with equal probability. So A or B in the AB basis, or alpha and beta. That's a misprint. That should be alpha. But back in the days, they had typewriters, not computers. So there's a lot of typos, and they can't fix the typos. So the alpha or beta in the alpha beta basis. And so,
okay, yeah. So in terms of the encoding, but then once they have this, I don't understand what they do with it.
So the serial number is, so if I haven't misunderstood this, the serial number is what is either this 0 or is a string of zeros or ones. And it will be, but it won't tell you what basis. And you have to measure in the right basis to get the right serial number. And so the right basis, so the right meaning for each qubit, which basis that qubit was encoded in originally, is known by the person who truly owns the money and the bank. So as long as those are kept secret, if someone tries to counterfeit the money, like even if someone were to steal the money, like steal the qubits, if they don't know the right bases, then if they just randomly guess the bases, they'll have some chance of changing the state of the money and therefore invalidate the money.
Okay, yeah, thank you.
No problem. So actually, the next question on the scavenger hunt is about the math of that. So we have a someone pretend to be a counterfeiter and say what happens mathematically if the wrong bases are used. What is the chances that the counterfeiter will succeed? Just in the naive way. You don't have to think about fancy strategies.
It's probably 0.2373, 23.7% chance, I guess. Around.
That's great. Where did that number come from? Sorry, you'll have to explain a bit.
Yeah, it's actually there in page number 80, the page 85, the last 3 lines of the first para. It's explained. I mean, I cannot clearly explain or give you the feel because I just saw those 3 lines, and if you see 3/4 to the power 20, so it is coming from there actually. But I myself am not clear. I just got the answer somehow.
I think in the paper they also mentioned a quarter chance of probability of getting things wrong at some point.
Yes, so you have two bases, and if you're just trying to counterfeit it, you have to guess a basis. So with a 50% chance, you guess the wrong bases,
Yeah.
and you measure in the wrong bases. And by this, you change the state. But then if the bank checks the money, they will measure it in the basis that they originally encoded it in. And now that you've changed it to a basis state of the other basis, they have a 50% chance of still measuring it correctly in the state that they produced it in. So you have a 50% chance of guessing it right, and then the bank has a 50% chance of still measuring it right, even if you guessed it wrong. And so you have a 3/4, this 3 over 4 in the paper. This is then the probability that the coin passes the inspection. And this is why.
Thanks, Julia, for the clarification. Is that all? Did that make sense? We can walk through this because this is the most important part of the paper. So, if anyone doesn't feel clear on this, we can spend more time on walking through specific examples. Just type in chat or just unmute if you have any questions.
So I have a question. Say the hacker or whoever, they guess wrong, and also now the bank has a 50% chance of getting it right, I guess, because the hacker gets it wrong. So what if the bank gets it wrong in that 50% chance? So what happens to the is it lost? Is it lost data or?
Yeah, so it's lost what the original value, so the original n sub I was, because the mi's are the bases, and then the n sub i's are the thing to check of the money, so the serial number, I guess. Then if say there was an evil bank that wanted to, Bank B is evil and wanted to steal Bank A's money by doing this attack, so Bank B is the counterfeiter in this case. If Bank B guesses any of the coins wrong, any of the bases wrong, then in a principle in quantum mechanics is that any attempt to observe a quantum state can change the state. So what that means in a quantum information sense is that if you use the wrong basis, you will actually change the state into be one of the states in that basis. And so therefore you will have no idea what the original basis was, or what the state in the original basis was. To illustrate that, I'm not sharing screen, but I could show the block sphere from before. Thought it'd be good to introduce the block sphere a bit at a time, so it's not all at once. But this sphere from before, the reason why it's quantum information scientists like to use it is because I'm zooming in. There we go. No, that's too much. It's because you don't only have to visualize states that are just in the directions. You can have vectors that are all different colors. So I'll show here. You can have a vector. If you were to have a vector, say over here, and you were to measure in the 0, 1 basis, then the probability of measuring 0 would be some related to this angle between this green vector and this blue vector that's pointing upwards. And the probability of measuring 1 would be related to this angle that's between this green vector and this green vector pointing downwards. So since this green vector is closer, this angle smaller to the 0 than the 1 state, then the probability of measuring the 0 state is higher. But since the plus and minus states are on the equator, So they're exactly halfway between the 0 state and the 1 state. Then you have equal probability of seeing 0 and 1 when you measure in the 0, 1 basis, one of the plus or minus states. And so if you had something originally in the plus state and you then measured in the 0, 1 basis, with 50% probability, you'll see the 0 state. And with 50% probability, you'll see the 1 state. And you will never see the plus state, and you'll lose the information that it was in the plus state rather than the minus state. And so this event in physics is called complementary observables, and it means that if you were to measure in, so let's say measure in 0, 1, then measure in, I'm using M for measure, then in plus minus, and then the fact that you did measurements in two bases complementary to each other, so complementary just means that in the block sphere sense they're on the equator with respect to each other. So if you were to turn this whole block sphere, like just tilt your head 90 degrees sideways, then you could think of this as the equator. And now it's like 0 and 1 are on the equator, so mutually unbiased with respect to the plus and the minus states. So that's a visual way of thinking about this. And so if you originally had something in the plus state, then just, it could be any of these states because these are all, in this case, it doesn't matter, one of these 4 states, and then you measure in the opposite basis of, so the basis that's not the one that's encoded in, then you measure in the original basis, you'll get 50% plus and 50% minus. So you've lost entirely the information that it was encoded in the plus state rather than the minus state in the first place. So this plus state means Ni equals 0. But now Ni is going to be 0 with 50% probability and 1 with 50% probability if you chose the wrong basis here. So you had a 50% probability here of choosing the wrong basis, doing this measurement, and then when the bank verifies here, then the bank will get the wrong serial number with half chance. So this 50% times this 50% of the wrong chance, 50% times 50% is 1/4, so 25%. And so you have, for every single qubit, a counterfeiter has a 25% of changing the value of the qubit and therefore changing what the bank sees, which is terrible. Because then that's just like, you'd have to win the lottery in order to steal money now. It's very difficult. I hope that answers the question. Yeah, so if you get the basis wrong, you destroy the information. So you destroy the information about what n sub I was, and just leave it up to chance.
I just have a question then in measurements in general, but if getting the basis wrong means that we're destroying information, it means that every time we're doing measurements, we have to be certain in which basis the state we're measuring is going to be informative. Okay. Isn't that a problem in information processing?
It's a problem depending on what you're trying to do. But for quantum computing, it's a feature, not a bug. It's something computer science like to say. So you can use these properties of quantum information to do cool things that you supposedly can't do on classical computers. So we'll probably cover that in a future topic, future journal club session. I'm pretty sure of that. All right, I think we can move on to question 5. But if anyone has any questions about anything so far, feel free to interrupt at any time. And the goal of today is not to get through all of the paper, since the idea is just so we get through most of the paper together, and then because there's always going to be really interesting parts of the paper, and you don't have to read or understand every part of every paper because that would just be too much. But if you get most of it, you'll be really set to read more papers after that, and it'll become much easier as you go on.
I
Oh,
have a
yeah.
question. So, are there any methods to further reduce the probability of the counterfeit getting the information? So, can we encode the say encoded message again? So, would that be a possibility? I mean, since we can't measure it, I mean, we have to do it without measuring. So that's the.
Yeah, this is definitely beyond the scope of this paper, but I will say that, oh, I'm still presenting, good. So I did see a paper about this, although I didn't read the math, but it's just a bit more math. But conceptually, it is very simple. Let's say instead of just red and green, we had a third color. I don't think what color would be good. Maybe light blue? Okay. So you might have heard for qubits, you have the Z and X and Y. So you have 3 poly operations, and technically you also have the identity, so that's a 4th one, but the identity is just doing nothing. So many people just leave that out. But let's say we also had the 2 states called I and negative I. Kind of how I'm drawing this here, and I might have gotten what the conventions for positions are wrong, although it's just convention, so I guess there's no wrong answer. So I and negative I here, they're it might be hard to see, but they're basically on the front of the sphere, like out of the page, and then the back of the sphere inside the page, like into the page. And so think of this as X, Y, and Z in 3 dimensions, and they do correspond. They're literally called the poly X, Y, and Z operators. To flip these into, those are the basic states for them. This is group theory, so this is really Bavitha's thing. That's what she studies a lot of and is very fluent in. So I'm a bit hesitant to. I'm not an expert in group theory, but in group theory, this is just for fun. In group theory, these quantum states, the complex numbers 2x2 matrices that are the group theory word would be special unitary 2, so SU2. So those poly matrices are important to that. And then the block sphere is in 3D space. So rotations in 3D space are 3x3 matrices that are the SO3 group. So we can say that we can have these I and negative I represent the Y basis. And then I'll change colors. The red and green bases. Oh, okay, I should have colored this bit differently, but let's say like X and Z. So 0, 1, plus, minus are for X and Z, and then okay, actually Z is 0, 1, and I'm going to change colors here because I don't think how we've done this. There we go. Okay. Plus and minus. So plus and minus are X basis states, and yeah. I was changing the colors. The point is that you can, in diagrams, use different colors to represent different bases. That's what my research is in, though it's a bit more than that. And then, so you can have these bases that are all complementary with respect to each other. So if you take any 2 of the X, Y, and Z bases, then you'll have this property, these things down here. In quantum computing, you'll usually just see the X and Z bases because those matrices are over the real numbers, whereas oh, I forgot some dot here. For the I and the Y bases, like these I and the dot wasn't showing up. Okay, the I and Yeah, negative I states, that's an I. Those are complex numbers, so people computationally for qubits just like to do X and Z bases. Yeah, that's. I think I hope that answers the question. Then, oh yeah, sorry, I didn't answer the question. So, if you have 3 different complementary bases, so you encode in not just the X and Z bases, but also X, Y, and Z for qubits, then you can get even stronger, even better results. So even lower than 1/4, because you're now taking advantage of 3 different bases. And so the number of values then becomes, you first choose one of 3 bases, and then you choose one of 2 states within that basis. So you can, the math gets harder, so I don't know it off the top of my head. And even if I did, this would not be the time or place for it. Also, some of my research is in qubits. So this is, although bit just means like either 0 or 1, classically, or quantum. So for quantum qubits, you can have stuff between 0 and 1, like a superposition, like the plus state is. So if this is the 0 state and this is the 1 state, the plus state is exactly halfway between 0 and 1 in this sense. So you can actually have 3 energy levels for qubits. So it just means that you can have a 0 state, a 1 state, and a 2 state. And then the math becomes a lot more difficult. And it's not really well known in computer science, like what to do once you have 3 possible numbers for each digit instead of just binary, because it's not something that would be useful, very useful in a classical computer setting, but in a quantum computer setting, it does reduce noise because quantum computers are noisy. I think there's questions in chat, and by the way, this stuff is like beyond the scope of the current paper, but it's always cool to talk about connections to present day and other stuff.
Yeah, I was just a bit confused about what you mentioned. I thought you mentioned like in some places you have 3 basis vectors, but in that case, how could you have them in a 2D space?
Yeah, so the answer is it's that you technically, like, SU2 is connected to SO3, so you have a block sphere, and the sphere is in 3D. So you have X, Y, and Z orthogonal, like, directions. But there's something called a global phase. And so if you visualize on a block sphere, then the global phase, think of it as going around the circle. If you ignore the I and minus I for now, then you just have a circle. If you just like the thing that is exactly flat to the page, so not the sphere, part of the sphere is coming out and into the page. And we can think of this global phase as going around the sphere. Let's say we're going...
I thought we didn't care about the global phase.
So the global phase doesn't matter if you have just a single qubit by itself, because when you measure, the global phase information doesn't affect the measurement results.
Yeah.
But if you have more complicated stuff, multiple qubits entangling and that kind of stuff, then if you have a global phase in one qubit, but it's entangled with a different qubit, then that global phase on just that one qubit becomes a local phase, and then you have to correct for it. So if you do one good example of that is if you do a controlled NOT gate, a controlled phase gate. So instead of a controlled NOT gate, a C-NOT gate. You can also do a controlled phase gate where you conditionally apply a phase.
Yes.
And so the definition of that, you actually need a phase gate on the control qubit to correct for that. It'd probably be good to just do that. That's definitely outside of the scope of currently, so I don't think we could do that succinctly to talk about that. But the phase part information is important. So although for experimentalists, you often can ignore and just not think about the global phase. For theory, it does matter because it can make a difference between whether something works or doesn't work if you have to keep track of these. Yeah, so I think that would be a good time to ask if anyone has any more questions, and we can just stick around for a lot longer. But we've gone through the scavenger hunt, which and in the future, this scavenger hunt we did together, but in the future scavenger hunts you could do in advance or do with your groups in breakout rooms, and we'll send up a follow-up survey to ask how the difficulty was on this paper and these questions so that we can get a sense of how to plan better for future ones.
I have just another quite silly question, but so we know that the probability is like something around 0.0034 or something. It was pretty low for the counterfeit to actually get the correct sequence. But so here's the thing. So this was on one sequence. What if they tried the exact same procedure on the multiple sequences, like multiple codes? So like it would become like a binomial probability, right? And the probability would increase, right? So if they have a machine which just goes through like all of the, like a lot of the codes, you know, the how do you say, like it just tries the same combination with a lot of the codes, then like the probability would be much more than 0 point, like the one in the paper. I hope I'm clear.
Yeah, I think I understand your question. So in cryptography words, this would be called a denial of service attack. So actually, first it's called a man in the middle attack because like someone like A and B in cryptography, they're always called like Alice and Bob, are trying to get a message to each other or trying to share, in this case, communicate about to verify the money, and then some evil eavesdropper or attacker in cryptography, it's called Eve. Usually just like they're just named that way. He's like in the man in the middle, someone in the middle trying to intercept that communication and mess with it to get information out of it. So in this case, the man in the middle attack, if Eve just keeps doing that over and over again, then Alice and Bob will first of all know that there's something terribly wrong because they can detect it. Not unlike with classical cryptography, if someone breaks your encryption, no one will know. That's very scary. Hopefully no one will break your encryption, but it's probabilistic. And if someone does, if you copy classical data, you can't know if it was copied, versus with quantum data, there doesn't exist a copy operation in quantum information unless you know the basis. But if you know the basis, then it just means you got really lucky to guess the right basis. So in the case of Eve doing a man in the middle attack too many times, if Alice and Bob notice, like in this case, the person who owns the money in the bank notice that there's too much discrepancy, then they can start have a new channel of communication or some other quantum channel that is not. So they'll basically realize that this channel is not secure and just not worth using. If Eve always had access to the whatever channel that they were using, then Eve can perform a denial of service attack in this way. So in this case, they're not really getting the money. That won't happen, but at least they can stop the money from being usable. But then it just becomes very annoying at that point. So denial of service attack, DOS attack. Maybe you've heard about some websites just on the internet where they get DOS attacks and then DOS. Yeah, so it's just like you can't use a website because that website's being attacked by too much, like say, computational power or useless, just garbage instructions to it at once, and so it's not able to perform what its services were supposed to be. I think there are future protocols, or at least for quantum communication, which basically takes this idea but scales it up to quantum secret messages, if that's the right word for it. They could take this into consideration. So, but that's more of an implementation detail, actually. And I think people have better things to do than do DOS attacks. Because the chance, if it's not great to justify trying to steal money if you know that if you can calculate the exact probability you'll succeed, and it's like really, really low. But this is one concern with quantum channels, is that there could be noise or DOS attacks in the middle. So this is why there would need to be a lot of different channels. I say channels, I didn't say what they were. So they could be like, Google tried to experiment with like microfibers under one city in the US. But in the US, it's not that much research in quantum communication. I think in Europe, there's a lot. And in China, there's a lot. With Europe, they sent election results via like, I think some kind of microfiber system, but I'm not too sure. And then in China, they had satellites send photons through space from like one side of China to the other, like east to. I don't know if it was east to west or west to east.
I was wondering, could we, I don't know, maybe sum up, like, because I was a bit confused reading the paper on the definition of like conjugate variables, and I felt that was a very key and important thing. So it's on, I mean, they mentioned them on like top of page 86.
Yeah, that's pretty good. Would someone be willing to explain the Heisenberg uncertainty principle? Just because that's related, I can do it as well.
So there's just a law in physics. So I don't know if you're actually asking about the conjugate variables or the conjugate basis that he's introducing in the paper.
I was asking about the conjugate variables because that's what they mentioned at page 86, and I was not really sure what it meant.
All right. Okay, so there are certain quantities in physics that obey just an inequality, that the uncertainty that you have on any measurement that you do is greater than a certain value, the product of these. So you can never have zero uncertainty on both your measurements of these two variables that you measure. For example, what he says also is position and momentum of a particle. So
so they're the ones that live in the same Hilbert space. No?
If I may, so like what Yulia said, these conjugate variables, to give a much more general definition, would be to say that they are the Fourier transform of each other.
I don't. Yeah. Okay. If you.
Yeah. Yeah. So that's why.
I didn't know if that was helping.
Yeah. And so, like you were also asking whether they are living in the Hilbert space. That kind of comes down to linear algebra. You don't actually say that the operator lives in the Hilbert space. I think they live on L2.
So we actually say that when you say something lives in a Hilbert space, we mean the states and not the observable that we measure.
It's more like acts on the Hilbert space than lives in the Hilbert space.
And of course, they form a new vector space on their own, but that's not the space that we're talking about.
Yeah.
We're saying it's the space of blah, blah, blah.
Yeah.
Maybe you should have like a basis course for a bit of linear algebra and, I don't know, Stern-Gerlach experiment for what does it mean to measure in a certain basis, and why do we have like just two states, but then we have X, Y, and Z, and it's all different bases. I think it was a bit confusing for some people today.
Yeah.
I love the project though. I didn't just want to critique now.
Yeah, it's okay.
It's a great thing.
Like, yeah, it is quite obvious because since a lot of people are coming from different backgrounds, some people would know this whole idea about this like spin and the different measurement bases and why it's differing, but they probably wouldn't know about the basic idea of classical cryptography, while the others would know this but wouldn't know the measurement. So like I think we can still find a way to kind of like bridge that. Yeah. Yeah, we could include something on a measurement basis. And I think it's quite confusing for a lot of people who starts when you say that you have to change from basis, the computational basis to, let's say, Hadamard basis to measure X. Not a lot of people actually goes back to thinking about the spin basis, and you don't have this whole thing. You can't know everything, that thing.
Yeah, sure. I'm also a bit, prejudiced by the physics background.
Yeah. Yeah. So, do we have any other questions? Or like, what do you have any other feedback, or which parts you had any difficulties, and feel free to speak about it.
I think we can stop recording before feedback.
Yeah, sure.
Just so, just letting you know, the feedback would definitely not go on YouTube, just because.
Yeah.
You can cut it.
That's gonna
Alberto.
I mean, I was a little bit struggling with the actual proof in the end. Partly because I don't know the notations like this. But that, yeah.
Yeah, we weren't sure if so most of this paper is extremely readable for beginners, but the very end does have some notation heavy stuff, so we weren't sure if it was the best idea to go through this at the very first session.
Yeah.
Without going.
I know most of the notation that's used there, but like certain specific stuff is very weird, at least to me, so I don't know how to deal with that. So for example, the I don't know, the squiggly bracket, I know they have different names, but I don't know how to translate them. So like
Oh, okay. The squiggly bracket is a common used notation for when you're denoting a basis, because it's, say you have a set, and so a basis is a set of,
yes,
in this case, a set of vectors.
Yes. So what does the exponent alpha do there? I don't know what that does in a set.
Here, alpha is not an exponent, but it's an index. So in physics notation, you might see in indices like this, and it just it's actually called Einstein summation indices sometimes.
Yeah,
so
I just didn't make the connection. Yeah.
Yeah, you use that to notate a specific element of a set where you can iterate over the set. In this case, you can iterate over alpha equals 1. The people from computer science background might find that very readable as well. Once you realize.
Yeah, now it makes fully sense. Like I just thought like what are the exponents doing there, and then I didn't read further, and then I like on page 88 in the beginning you can clearly see its Einstein notation. Yeah. Okay. Thank you.
We can wait a few more seconds for questions, but also thank you all for showing today and like being interested in learning more. Like this will typically being proactive to take the leap to read papers and meet strangers online to talk about them is definitely going to get you very far. I can say that. Feel free to ask more questions, and if you think of questions later or have questions about the next paper, or any paper, you can always ask in our Discord server. Whichever channel, there's a few questions related channels, so learn together probably would be the best number of text channels. So quantum help, programming help, and ask anything to ask questions in.
Yeah, and I want to add something. So a lot of people were able to engage in discussion and speak about it and discuss the results, and some of you didn't. Probably you chose not to, or do not worry if you found it a bit difficult to go through and this is the first quantum related paper that you read. it's still fine. And the more exposure you get to these words, these key terms, the kind of notations used, the better you'll be able to read the next papers. And also, you really don't have to wait till the sessions to ask these questions. You can, like, while you are reading the paper, if you have any, like what was mentioned before, any notational confusions, you could like directly come and ask for it in the Discord channels. I'm pretty sure like there is always someone to help you out there, and you can ask questions while you are reading it instead of like waiting till the session. And from the next week onwards, we are hoping to have it more interactive and like let everyone speak with each other. And thank you very much for participating. And Lia, thank you so much for the nice session today and for preparing that scavenger hunt. And let's meet everyone again next month. And if you have any paper suggestions, do come and mention it in our Discord channel. We will look into it, and we will also give you more options to choose from for your next sessions. And do consider, if you wish to present something on your own, we are more than happy to have
Or in a
session with
group.
you.
Doesn't have to be on your own.
Yeah. But there is no rush. You can go at your own pace. So
Yeah.
if you wish, you just know that you always have the option to do that.
Also, if you've written down just your solutions to the scavenger hunt and you'd like to send them in, for example, we can post them anonymously or not, so that future people can also go through the scavenger hunt through these seminal papers. First without an answer key, sort of, and also with an answer key later to reference. That would be really helpful and a good educational resource. And you could get a t-shirt. You would get a t-shirt if you worked on that. Because we have them, we have money from a nonprofit, so we should spend them on free t-shirts because they're cool. Yeah, thank you, everyone.
Sorry, I did not fully understand this thing about scavenger hunt. Can you briefly explain this again?
Yeah, so it's a link. It's linked as a PDF that you can download in the calendar invite and also posted in the Discord server. So it's called a scavenger hunt because it's a scavenger hunt through the paper. So it was the questions I had on the right hand of the screen while you were going through today's session. And the idea is that you can read some questions that will guide you towards the main points of the paper so that you don't have to be worried about all the little things that you might get stuck on in various areas, and plus, that way we can have a discussion about the same questions rather than all over the place to tell a story, go through the story of the paper. If you're not able to find the PDF for the scavenger hunt, let us know. It's in the Discord server.
Okay, I understood. It was the paper we read just now, the PDF, 2 pages PDF you... Okay, I didn't
The
get
one with
its name.
questions. Thank you very much for all the reviews. We are also excited for the next session. And if you have any feedbacks, you can send them in Discord as well. We want to keep improving this so that it is really helpful for the beginners. That's like our target group. So we want to know the kind of difficulties you would face so that we can adapt it accordingly. So you can contact me directly if you want to like be private about the problems you faced. You can speak with Lia or Alberto or anyone in our Discord channel which you can see, and with the tags admin or contributor or curator. Or else like you could just, if you're okay with it, you can also post it publicly and we will edit the video and have it on YouTube channel. So yeah, the scavenger hunt is actually already on Discord channel. I think Nisha, you should be able to download it. It's under the general channel under the journal club section. Okay then, so I think that's where it ends, and see you next month. But let's keep the conversation going on Discord. So bye everyone.